All right, welcome, welcome. No IP, no problem. Exfiltrating data behind IAP. We got my man, I said before, Israel's finest was here, but actually this is the Israel finest all the way, Ariel Kalman. Thank you, bro, for being here. Thanks all of our sponsors. We love you. Couldn't do it without your money. Cha-ching. Volunteers, you, all that shit. Adobe, Aikido, Drop Zone, blah, blah, blah. Profit Run Zero. No phones, please. Silence them. Don't be a dick. We're all here to hear amazing things. Questions at the end, maybe one or two, maybe none. We'll see. And no pictures either. Nobody likes that shit. You ready? Let's go.
Hello, everyone. Can you hear me? Welcome to my talk. Thank you. Welcome to my talk. No IP, no problem. Exfiltrating data behind IAP. First of all, I wanted to say thank you for joining me today. I hope the talk going to be both insightful and interesting too. So today's talk going to focus on one service in GCP called Identity-Aware Proxy. We'll explain what this service is, how it works, and how it can be abused by attackers to exfiltrate secrets. So my name is Ariel Kalman. I am a security researcher at Mitiga, and I came all the way from Tel Aviv, Israel. And a fun fact about me, because I had to, is that I prefer dogs over humans. So the agenda for today, we'll start by explaining what is Identity-Aware Proxy and how it works behind the scenes. Next, I'll show to you two IAP misconfigurations that we saw in the wild too many times. The next part will be a quick introduction to cross-origin resource sharing, a security feature in web browsers, and we'll explain how is it related to IAP and how it may allow attackers to exfiltrate secrets. And the last part, the most interesting one, is an IAP configuration that, if enabled, allow attackers to exfiltrate secrets from sensitive environments. So what is Identity-Aware Proxy? Identity-Aware Proxy is a service in GCP that acts like an identity firewall. It sits in front of your application and intercepts any request to that application. It controls the access to the apps based on identity. It blocks any unauthenticated request to the application by default. And it has some interesting settings that I will show to you later. So how IAP actually works. When the user tries to access an application, he sends the request, and the request hits the endpoint of the application. Because we enabled IAP to protect that application, IAP gets the request and checks if the request is authenticated or not. If the request to the application is unauthenticated, IAP, forwards the request, redirects the user to a Google Authenticator page. The user needs to put his email and password and log into his account. If the user was successfully logged in and authenticated, he then needs to be authorized to make sure he has sufficient roles to access the application. If he both authenticated and authorized, IAP injects the authentication headers to the request, and he can now access the application without fill IAP in the middle each time, because he now has the token on every request. So we understood what is IAP and how IAP works. Let's see two IAP misconfigurations. The first misconfiguration is overly broad IAM grants. When you use IAP to protect an application, you need to explicitly specify which users can access the app. And in GCP, we have two spatial member types. The first member type is all users, meaning every user in the world, no matter if it's authenticated or not. And the second member type is all authenticated users, meaning every authenticated user to a Google account, no matter if that account is part of the organization of yours or not. So adding one of these member types to the list of users that can access the application effectively disabled IAP, because now when the user gets to the authentication and authorization part, every user can go through, even an attacker. This is how it looks in the platform when you do this misconfiguration. Here you can see a screenshot of the Cloud Console, and you can see me adding all users member type to the list of users that can access the application. When I do that action, I get a warning saying adding all users makes this resource public and accessible to anyone on the internet. However, when I do the exact same thing via the G-Cloud CLI, I get no warning, and the operation just executed quickly. So it emphasizes how easy it is to make such mistakes that effectively disable the IAP. The second misconfiguration is exposing a bypass path around IAP. As many of you know, many applications have multiple endpoints. And when you use IAP to protect an application, you need to explicitly enable it for each endpoint. If for some reason an admin mistakenly forget one endpoint and didn't enable IAP for that endpoint, this endpoint is not protected, and attackers can sneak in through that endpoint and access the same data of the application. This is just a diagram to show how it looks. You can see an attacker that tries to access the application, but it gets blocked by the IAP because he has no token to access the application. However, when he sends the exact same request to the other endpoint of the same application, he can access the same data, and IAP don't protect this endpoint. So we saw two IAP misconfigurations. Now I want to do a deep dive into one risky setting on IAP that, if enabled, can allow attackers to exfiltrate secrets. So the name of the setting is allow HTTP options. And the description says control HTTP options course preflight. But to truly understand what this setting is, I want to first of all explain what is course and what is course preflight. So what is course origin resource sharing, or course? When you search it online, the first result that you see is saying it's something that's designed to annoy developers. It works by giving you errors, leaving you scratching your head. So while it's sometimes true, let's demystify it a bit and explain how it really works. So what usually happens when a user accesses a web page is that he sends a request to the application and gets back the response: HTML, JavaScript, CSS, and images. And sometimes, some of these resources are hosted on a different server on the internet. So to fetch these resources, JavaScript has a built-in function called fetch that fetches resources from a different server. It basically sends another request, cross origin 1, to that server asking for that resource. But imagine what happened if instead of that legit JavaScript that fetches an image, you get a malicious JavaScript code that tries to fetch sensitive information from your bank account server. You want to block this kind of attacks, and this is why most browsers today have a built-in security feature called same origin policy that basically prevents websites from accessing other websites' data without their permission. So when the bank server will get the request, he will check if he wants to allow the origin to access this data or not. And then he will respond with a special header called access control allow origin. And keep that header in mind because it will be an integral part of the attack that I will show later. So the bank server gets the request, check if he wants to allow it to access the data or not, and respond with that header containing a domain, which is the origin that he wants to allow it to access the data, the origin that made the request. My browser gets back the response. It checks if the origin that made the request is equal to the value in that response in the header. If they are equal, he allows us to access the data. And if they are not equal, he drops the response. So this is how this kind of attacks can be mitigated by the browser security feature called same origin policy. But now let's take it one step further. Imagine that instead of that malicious JavaScript code that tries to fetch sensitive information from the bank server, you get a malicious JavaScript code that tries to send post request instead of get request to the same server and trying to execute money transfer operation from account A to account B. Because the bank server will get the request and execute the operation before my browser will get back the response, this kind of attack cannot be prevented by the same mitigation that I just showed you because it's too late. Now the operation of the money transfer already happened when the browser gets back the response. So to solve this kind of issues, same origin policy has another kind of solution that's called course preflight. And course preflight is a special type of HTTP options request that is sent by the browser before the real request. We basically ask the bank server, is this request allowed or not? If the browser says yes, we send the real request, the original request that we wanted to send. And if the browser says no, if the server, says no, my browser doesn't send the real request. And one key note to know about this kind of HTTP options request is that it's unauthenticated. And this is by design. This process of communication between the browser, asking the server, is this allowed or not, this process is supposed to be lightweight and simple, and we cannot change it. This is how it works, and this is mandatory. So that's it. I explained what is IAP, what is CORS, excuse me, and what is CORS preflight. Now let's get back to the setting and explain what happens if we enable that setting on GCP. So again, the name of the setting is allow HTTP options. So, like we said in the beginning, when the user sends requests to the application, if they are unauthenticated, it blocks by the IAP immediately. And preflight requests are unauthenticated. So it means that every request from the user to the application, which is unauthenticated, including these HTTP options requests, are blocked by the IAP when you use it to protect an application. And this prevents applications that use CORS from working behind IAP. And this is why GCP added a security feature, a security setting to IAP that can be either enabled or disabled. And if enabled, it allows only HTTP options requests to go through IAP without authentication, reach the application, and let the response get back to the user. Every other request, every GET, POST, or other type of HTTP request to the application is still blocked by the IAP. This is how it looks before we enable the setting. You can see that the user sends a simple HTTP options request to the application, but it gets blocked by the IAP because it's unauthenticated. And after we enable the setting, we send the exact same request to the application, and we get back the response. So this is how it works. And you can see inside the response a special header that I explained earlier, access control allow origin. And this header is supposed to contain the domains that are supposed to access the information inside that resource on the web server. And now I want you to think like an attacker. What if the attacker can control that response? Like what if the attacker can put some value that he wants to exfiltrate instead of that example.com and exfiltrate this as the secret? So this will be the exact attack that I'm about to show. So before I'm explaining the attack step by step, I want to explain the prerequisites and the diagram. So this kind of attack has a few prerequisites to work. The first prerequisite is that we have an application and we have IAP that protects that application. And the setting that we showed, allow HTTP options, is enabled on the IAP. The second prerequisite is that the attacker has some kind of initial foothold inside the environment. It can be any form of code execution mechanism. It can be a VM, a Cloud Run, a Lambda function, anything that can be used to execute commands. And we have an identity with the role app-engine.deployer, which is a very common role being given to developers that need to deploy their new versions to their applications. And we also have this external attacker, which is just a VM on the internet. And our goal is to exfiltrate a secret from the internal attacker to the external attacker. But we cannot just send in packets directly from the internal attacker to the external attacker because this environment is very restricted. Like no outbound access is allowed, and the external attacker cannot access any resource from the inside because IAP protects the application, and any other resource is accessible only via private access. So the first step of the attack is that the internal attacker deploys a new version to the application. It's just a configuration file, a YAML file, containing multiple configurations of the application. And this is how it looks. And inside that YAML file, it can put a value in the access control allow origin that practically defined what domains should the web server answer to if someone sent HTTP options request to that server asking for which domains can access the resource using CORS. So here the internal attacker put a secret inside that value, and this is the secret that he wants to exfiltrate. In this case, I put shrug, but it can be any kind of secret. It can be any kind of secret, token or certificate, anything that can be encoded into characters. The second step of the attack is that the external attacker sent an HTTP options request to the web server. Because we allowed the allow HTTP options setting on IAP, this request can go through IAP and reach the application. The external attacker doesn't need any token to send this request and get to the application. And this is how this request looks like. The third step and last step is that we get the response. The app engine responded with the response to the HTTP options request, and inside the response, you can see that the value that we wanted to exfiltrate. This is from the screen of the external attacker. So it means that the internal attacker was able to exfiltrate that shrug to the external attacker without sending a direct packet. So this process can be automated to happen over and over. The internal attacker deploys a new version with a new secret, and then the external attacker fetch it from the outside. And the internal attacker deploys a new version with a new secret, and the external attacker fetch it from the outside. And I was able to automate this process just out of curiosity to see how much data I can exfiltrate. And I was able to exfiltrate 15 megabytes of data during one day. And I know it doesn't sound like a much, but it's enough to exfiltrate secrets, tokens, and certificates that can be later used by the external attacker to expand the attack surface to the environment and access more resources and like expand the attack. So that's all. And now let's see how it looks in the logs when you want to detect this kind of attack. When you automate this attack, you expect to see a spike in the number of operations, and you can see that the same operation happened over and over. Every 30 seconds, user 0 deployed a new version to the application. This is the first step of the attack. And the event name is create version on App Engine. And this is a very weird activity because no developer needs to deploy a new version to his application every 30 seconds. And this is why it's so easy to detect. You can see here an example of a detection that detects this kind of attack. And this is the only detection you need for this kind of attack, and the only detection you can write for this attack, because the only part which is logged is the first step of the attack, where the internal attacker deploys a new version. The detection combines of 3 steps only. The first step is to filter the relevant event, in this case, create version on App Engine. The second step is to group by the number of events, define some time window, and count the number of times this event happened during that time window. And the third step is to filter the number of, the amount of times this event happened. So before I do a quick recap, I just wanted to say that we disclosed this behavior to GCP, and they acknowledged this issue, decided to currently put an update on the documentation of IAP to highlight the risk of enabling this feature, but they decided to not fix the issue right now, maybe in the future. So a quick recap, I showed you what is identity-aware proxy, how it works in reality, and what is cross-origin resource sharing, and how they are both can be related. I showed you 2 IAP misconfigurations that are relevant not only for this kind of scenario, relevant to more services and resources in GCP, like the first misconfiguration of all users and all authenticated users. This is a misconfiguration that is relevant for practically every service in GCP that defines access. So you should check this out and look at your environment to see if it's relevant for you. I showed you how you can abuse one setting on IAP to exfiltrate secrets, and how you can detect it. Thank you so much for listening, and I'm open to take any questions if you have. Hmm?
Wait, come here. I'm sorry. I broke the microphone. Sorry, guys. Come over here. We got time for another one if anybody wants to come up here. We got one more.
Yep, thank you for the talk. If I understand well, for the data exfiltration, you need to reconfigure the app engine. I would like to know the difference of privileges needed to redeploy a configuration on the app engine and the privilege needed for the IAP global modifications. So, for example, or usually users that can redeploy configuration on App Engine has enough privileges to just modify the IAP configuration and go from all authenticated user to all user policy.
Yeah, so the only permission that you need to deploy a new version to the App Engine is the App Engine deployer. But you asked about the IAP configuration. And we don't assume in this attack that the attacker actually changed the allow HTTP option setting from disabled to enabled. We assume that this is the environment and the allow HTTP options is enabled. And we highlight the risk of that behavior if like an admin used that setting. So the attacker doesn't need any permission to change the IAP configuration, but he needs the permission, the App Engine deployer, permission to change the App Engine configuration, this YAML file.
Okay. And the privileges regarding the App Engine deployer is usually granted to a larger population that...
Can you repeat?
The IAP engine deployer privileges is usually granted to a larger population than just IAP.
Yeah, so most developers that use App Engine to deploy their versions needs this role to like access the resources, deploy new versions, and mess with the application. So it's a very common role being given to developers, and this is why it's a bit risky. Yeah, thank you.
Anyone else? We got a minute or two. Come on down. Price is Right. That's a game show for you young people, although y'all look a little old out there. And I didn't break the microphone for the record. It was already broke. No questions. Sheesh. All right. Everybody give it up for Ariel.
Thank you.